Okay, good day. So today we will be discussing about second order differential equations. Okay, so when we say second order differential equations, it is actually, okay, when we say from the word second order, okay, so so the highest level of differential will be second. So it will have what a term containing like this, okay, y double prime or d squared y over dx squared as its highest degree. Okay, so technically second order differential equations in linear form will have we have a general form called like this. Okay, so this is the general term for second order differential equations, where p of x, q of x, and r of x, and g of x are all functions of x. Okay, functions that contains x. But somehow, okay, so in this case, if gx, okay, so if the gx here is equal to 0, it will be a homogeneous differential equation. So other than that, okay, so other than that, so if g of x is not equal to 0, so there is another term. So this is what we call non-homogeneous differential equation. Okay. So that is how, okay? So we divide second order linear differential equation into homogeneous differential equations and then non-homogeneous differential equations. Okay, so this is not only for second order differential equations but in nth order differential equations in general. So if gx is equal to 0, it's homogeneous. And if not, it's not equal to 0, then it's a non-homogeneous second order. Okay, so there is a second order here. Okay, so that's how is second order differential equations. Okay, okay. Somehow, not all second order differential equations could be solved in an elementary manner, okay, in a basic manner. Okay, so one criteria that we can solve, okay, so if p of x, q of x, okay, so there is y here, okay, so sorry, so I forgot to put y. So p of x, q of x, and r of x are constants. So that will be the time that there is an elementary solution. Okay, elementary solution. Okay, so we call it an elementary solution because it is relatively easy. Okay, so we can discuss it today. Okay, so nevertheless, Okay, so we will proceed. So we know now homogeneous differential equation and non-homogeneous differential equation. So when we say constants, okay, so just a review, if we say constants, it are numbers, okay, such as 1 point, okay, general number, so constants that are non-imaginary, all real numbers. Okay. So one thing is we will going to concentrate on homogeneous second order differential equations. Okay. So let us have some examples of second order linear differential equations. Okay. So examples. Okay. Okay. So this is an example of second order linear differential equations. Okay. So why we say it's linear? Okay. So as you can see, it is in diminishing degree of differential equations. Okay. So we know that its highest degree is 2, so therefore it's second order. So other than that, if it's d to the power of 3 over d over x to the cube, then it will be the third order. So if it will be d to the power of 4 over dx to the power of 4, so it will be fourth order, and so on. Okay. So since the highest degree is 2, okay, so therefore it is second degree linear differential equation. Okay, so you can actually represent it as this one. Okay, so instead of this, so they are just same representation. Okay, so this is a homogeneous. Okay, it is called homogeneous because its right hand is 0. But if it is not 0, let us say it equals to 8x is equal to 8x, for example, it will become non-homogeneous. Okay? But somehow we'll concentrate on homogeneous first. Okay? So what are the ways in order to solve homogeneous second order differential equation? So stay tuned. Okay, so we will solve that one. So there are actually 3 cases in order to solve a second order linear differential equation in homogeneous, okay, homogeneous second order linear differential equation. Okay, so there are actually 3 cases, but before that, we should know how to use auxiliary equations. Okay, so how to solve? So you might ask how to solve. Okay, so how to solve that one? So nothing. Okay, so let's have an example. So let us say this is our first example. Okay, so it's different from this. So the first thing you should do is to convert it into auxiliary equation. Okay. So in forming auxiliary equation, okay, so we should convert the differential term into an algebraic term. Okay, so let us say that y will be equivalent to 1, y single prime is equal to r, and then y double prime is equal to r squared, and so on. Okay, so if it will become y to the n, okay, third, for example, there is a third degree. So I am talking about general linear differential equations, not just second order, but linear. So it will become r cubed, and so on. So it is y differentiated n times, so it will become r to the power of n. Okay, so our goal here is to convert this second order linear differential equation into an algebraic function. So we can solve it like an algebra. Okay, so we concentrate on these three terms. Okay, so we let it. So therefore, if we replace all these terms to that one, so it will become r squared minus 8r plus 15 is equal to 0. Okay. So by now, we see that it is already a quadratic or an algebraic function or an algebraic equation, specifically quadratic equation. Okay, so the thing that we can do is we can solve it by using quadratic equation. So you can apply all this one. Okay, in which your a here is 1, b is negative 8, and c is equal to 15. Okay, so you can solve it algebraically. So from that, okay, so we can solve it. So we'll try solving it using the quadratic equation. Okay, so we all know that a, okay, so negative b here is negative 8, so negative 8 plus minus negative 8 squared minus 4, a is 1, and c is 15 over 2a. So the a here is 1. So therefore, you can solve it as 8 plus minus 64 minus 60 is equal to 4. Square root of 4 is 2. So therefore, we can get that there are 2 r's. So the one r is 5 and the other is 3. So you can also use factoring. Okay? So instead of using quadratic equation, you can also use factoring. Okay? So just a review. But somehow, if factoring does not works, your quadratic equation or quadratic solution for your quadratic equation, okay, your quadratic equation is always applicable to all, even if the roots of this equation is imaginary. So therefore, you will use r minus 5 times r minus 3 is equal to 0. So r is equal to 5 and r is equal to 3. So this is much shorter. Okay, so this is much shorter solution. So, okay, so either this one or this one is viable. Okay, so I just explain that you can use several methods to use to do this. So in this form, so this is actually case 1. Okay, so if the roots of auxiliary okay, equation. Okay, so maybe we have no space, so I will erase this one. Okay, so since it's that portion is redundant with the solution on this one, so this is actually case 1. So in case 1, so if auxiliary equation has two distinct roots, so in this one, it has two distinct roots in which two different roots. The other term for distinct is different. It has two different roots, so therefore your solution will be y is equal to c e to the power of r sub 1x and c sub 2 e to the power of sub 2x. So this is just a template in which you will replace it with the roots. So the r sub 1 here is 5 and the r sub 2 is 3. Okay, so please take note that the roots can interchange. So it could be that your r sub 1 and r sub 2 could interchange. It could be that your r sub 1 instead of 5 is 3 and your r sub 2 in terms of 3 is equal to 5. So it doesn't matter. Okay, so if your answer is the roots interchange, so it doesn't matter, it's still the same. Okay, it's still correct. So it will be, you will just replace it in this template. It will become c sub 1 e to the power of 5x plus c sub 2 e to the power of 3x. So this is your solution. Okay, so this is case 1. If auxiliary equations has two distinct roots. Okay, so please revisit this one. So this is case 1. And this is his solution. Okay. So please remember case 1. Okay. So there is actually case 2. Okay, so if there is case 1, there is actually case 2. Okay. So please, okay. So please you can screenshot this one or you can, okay. So I will erase this one so that we can proceed to case 2. Okay. So what is the case 2? Okay. So we will have another solution. Okay. So before we describe that case, what I mean by that case. Okay. So what if the equation is this? Okay. So obviously it will change. Okay. So if we replace in quadratic equation, okay, so it will be, to apply in this quadratic equation, so it will become, okay, negative 8 plus minus negative 8 squared minus 4 times 1 times 16 over 2 times 1. So it will become 8. 64 minus 4 times 16 is 0. So therefore, there is only one root, r4. But somehow, it has 2, okay? When we factor it, it will become r squared minus 8r plus 16. So if you use factoring instead to solve the problem, you will get the same. So therefore, your r is only one root, which is 4, but multiplicity of 2. Okay, so because it has two distinct roots, so this is now what we call the case 2. Okay, so case 2, if, okay, the auxiliary equation has two equal roots, okay? If it has two equal roots, then therefore, your solution will be y is equal to c1 e to the power of r plus c2x e to the power of r. So that the r here is only 1, which is 2, but somehow it is repeated twice, so therefore your solution will be y is equal to c1 e to the power of 4x, okay? So there is x here, plus c2 to the power x e to the power of 4x. So this will be your solution. Okay, so that will be your case 2. Okay. So what about case 3? Okay. So case 3 will be another story. Okay. So please take note of that. So paano yung case, so what is case 3? Okay. So what if, okay, so another solution, so let us make it 17 here. So this is another example, okay? So we will expect that this problem, okay, so this problem will actually yield a, okay, it will actually yield a imaginary roots. Okay, so that's why you can always use this quadratic equation in order to solve the problem rather, because sometimes the roots is imaginary. So we got r is equal to negative b, negative 8 plus minus negative 8 squared minus 4 times 1 times 17. So it over 2 times 1. So r will be 8 plus minus, so therefore it will be 64 minus 68, so therefore negative 4 over 2. Okay, so it's equivalent to 8 plus minus 2i over 2. So r is equal to 4 plus minus I. Okay. So case number 3. So we'll have case 3. So if the differential equation, okay, so if the auxiliary equation rather has two imaginary roots, let us say your imaginary roots r is equal to alpha plus minus beta I. Okay. So what is the solution of this? The solution will be y is equal to c1 e to the power of alpha x multiplied by c1 cosine alpha x plus c2 sine beta x. So this is the solution. So we could identify what is, okay, beta. This is also beta actually. So we could identify that the alpha here is 4 and the beta here is 1. Okay, from that, okay. So therefore, y is equal to e to the power of 4x c1 cosine x plus c2 sine x. So this will be your solution. Okay, so that is the 3 cases in solving the homogeneous differential equations or homogeneous second order linear differential equations.